Okay, let's talk about problems that will deal with VSPER and some bond angles. It's asking us to consider the nitrate ion, the NO3 minus, and then it's asking us what is the central atom. We can probably figure that one out right now. How many lone pairs are around the central atom? Probably have to do the Lewis dot to figure that out. What is the ideal angle between the nitrogen and oxygen bonds? And then might we expect, because of some geometry, maybe some lone pairs, maybe because of double bonds, might we expect something to be somewhat different. So let's see if we can do this in the NO3 minus anion. Okay, so let's go ahead and do the NO3 minus Lewis dot structure. Let's count the valence electrons. We got 5 from the nitrogen. We have 6 times 3, 18 from the oxygen. And then we'll have the 1 that comes along with the charge of the anion. And so that should equal 24 valence electrons that I have to consider when drawing the Lewis dot structure. And so let's put our nitrogen there in the middle. It's obvious that's going to be the middle. We got an oxygen coming off. We have an oxygen coming off. We have an oxygen coming off. And let's put in our valence electrons, complete the octets around the oxygens right here. Okay, and so far I have 8, 8, 8 around here. So I have my 24 taken care of. Okay, but I have a problem that I can see in the middle, and that's my nitrogen right here isn't a complete octet. And so what I can do is I can take a lone pair from there, and for my structure I can then write N double bond O with 2 lone pairs, and then I've got oxygen, and then I have oxygen coming off here. Okay, I still have 24 valence electrons, so this is a correct Lewis dot structure. I have an octet around that nitrogen, and so this would be a very good candidate for a Lewis dot structure. I'll go ahead and put that in those brackets with a minus charge, but you can see I have got 2 other possible resonance structures here. And so what I can do is go ahead and draw my resonance arrows, if you call that an arrow. And I can draw, again, the oxygen, nitrogen, oxygen, oxygen. But now I can put my double bond here. And so if I fill in my valence electrons around the terminal atoms here, then I also have, oops, I got that pair, so let's get rid of that pair. So I also have this as a valid resonance structure where the double bond comes up to this middle oxygen. I have a lone pair there and I have a lone pair there, so make sure I accentuate my mistake. And then we've got one more resonance structure that we can look at right here. And so I have an oxygen, nitrogen, oxygen, but this time the double bond will be on that right oxygen, and have those 2 lone pairs with 3 lone pairs around the other oxygens. Okay, so I have 3 resonance structures here. Now I have an A, meaning the central molecule here is nitrogen. I have X, which means that I have 3 atoms surrounding that central atom of nitrogen. So I have AX3, and I have a lone pair electrons of 0. So if you remember our AXE nomenclature, so this is going to be AX3. Now what is the geometry of this that you should have memorized, or you will have memorized? Let's go back to our PowerPoint right here. And so we see that if I have an AX3, this is trigonal planar, and my bond angles are going to be 120 degrees for the trigonal planar. Okay, now let's go back and look at our resonance structure here. These resonance structures would be something actually very, very equal. So if I was to draw kind of what this would really look like in real life, then we actually have a resonance structure that looks like those bonds are sharing all throughout here. There is going to be no deviation in our bond angles that we would expect. There's no lone pairs pushing them down. There's no double bonds that are creating a disproportionality within this particular molecule, and so we wouldn't expect our bond angles to change very much at all after looking from the ideal bond angles. Let's go back and answer our Alex question. What is the central atom? Well, we've just been drawing that. We know that it's nitrogen. How many lone pairs? There were no lone pairs around our central atom. What's the ideal bond angle? It is 120 degrees. We got that from our PowerPoint, and just from memorizing that for trigonal planar and AX3, that's going to be 120 degrees, and it's going to be about the same if we would expect anything to change between those nitrogen and oxygen bonds. We didn't see anything that was going to change that for us, and so when I go ahead and check this, then Alex should give us green and tell us that we're right, and it does do that.